So we've dealt with verifying the mass of our desired compound. We've dealt with identifying what functional groups are present in our desired compound. But so far, nothing has given us the tools to unambiguously assign the connectivity or the bonding in our compound of interest. Nuclear magnetic resonance is a technique that allows you to see the connectivity between carbons. Now, it's not a photograph of the structure of a molecule. There's actually experimental techniques for that, one called X-ray crystallography, but rather NMR provides data that you can use to infer the structure of a molecule. What we'll talk about today is just, and in the next two class periods, is just scratching the surface of what NMR is useful for. The technique is, we'll learn just a little bit of the physics, but this is a very, very useful technique. It's actually found uses in medicine, radiology, and imaging. So the technique, if you've ever heard of getting an MRI, magnetic resonance imaging, or if you saw that episode of, what was it, House, where the guy had a swordfish, was it House or was it The Good Doctor? I can't remember, where the guy had a swordfish stabbed in his leg and they tried to get him in the NMR, and then all the bait and lead pieces inside the swordfish exploded everywhere because the NMR was a magnet. Nobody knows what I'm talking about? Okay, whatever. MRI involves the same basic physics. We won't talk about MRI. You have to wait for your radiology class someday in medical school, but the fundamentals are based on the same physics. So, nuclear. What is nuclear? That has to do with the nucleus. And it turns out that nuclei, and everything we've done in this class has mostly been about electrons attacking empty orbitals. We've basically ignored the nuclei. But nuclei, like electrons, have a property called spin. And it's related to angular momentum. Now, with electrons, the possibilities for spin there are two of them. There's plus 1/2 or minus 1/2. That's the spin quantum number for electrons. For nuclei, it's a little bit more complicated because nuclei have two different kinds of particles in them, protons and neutrons, and each of them can have spin. We don't need to worry about the physics that causes this, but understand that you can think of most nuclei, many nuclei anyway, as having angular momentum. Some nuclei have spin 0, so that means they're not going to be NMR active. They're not going to be detectable by NMR. But a lot of nuclei have non-zero spin, and the most useful spin value a nucleus can have is 1/2. So it used to be thought that the spin of a nucleus was related to the spin of a nucleus is a property that's called angular momentum. And they used to think that the nucleus was actually spinning on an axis, and when a charged particle spins, it generates a magnetic field. We no longer think the nucleus is actually rotating, but it has a property called angular momentum in it. And each nucleus that has a non-zero spin has a magnetic field. So you can think of the nuclei of atoms as being little magnets that can respond to magnetic fields. Now, there are different nuclei with different spin values, but the simplest spin value a nucleus can have is spin 1/2. And this is true, fortunately, for a lot of the atoms that are relevant for organic compounds. And in particular, we're going to focus in on carbon and hydrogen, because if you have IR data and molecular weight data that tell you that nitrogens and oxygens are present, and you can identify some of the functional groups, possibly with the hydrogens and the carbons, you could piece together the connectivity of the molecule. Hydrogen 1, that is just regular proton, has a spin 1/2, and the abundance of hydrogen that isotope of hydrogen is almost 100%, which is really, really fortuitous, and I see the hand of God in it, that it just so happens that one of the most common atoms in organic molecules happens to be one that we can learn about through this technique. And then carbon, the other one that's most important, carbon-12, the most common isotope, is spin 0, but carbon-13 is spin 1/2. And carbon-13 has a much lower abundance than hydrogen. Carbon-13 has an abundance of about 1%, but that's enough to see in most samples. And so there are other kinds of NMR, fluorine, phosphorus, nitrogen NMR, and all of them are useful too, but we will focus on hydrogen and carbon NMR. Where did I don't know, there we go, good. Okay, so why does it matter that hydrogen nuclei are magnets? And you have to imagine you're looking at a sample of an organic molecule and you've got carbons, you've got hydrogens, they're bonded to each other. We're not talking about movement of the hydrogens around in any case. We're not talking about changing the way they're bonded. We're just zooming in to the really small nucleus and seeing what it's doing. When the hydrogen atom is a magnet, when it has a magnetic field, in the absence of any external magnetic field, the individual hydrogen magnets are going to be aligned in random directions. But in the presence of an external magnetic field, and in particular if that field is strong enough, there are going to be two possible, what we will call spin states for the hydrogen atom, the hydrogen nucleus. Its magnetic field, indicated by this little arrow, each of the gray dots is a hydrogen nucleus. We're not worrying about what they're bonded to. The arrows represent the alignment of the magnetic field of, or the spin of, the hydrogen nucleus. Each of those arrows can be aligned either with or against the external magnetic field. Two sort of discrete energy states that can be adopted. You can be aligned with or you can be aligned against. And this is an oversimplification of what's actually going on, but it's a simple enough and useful enough picture that that's what we're going to stick with. Turns out that being aligned with the external magnetic field is a lower energy state than being aligned against the external magnetic field. Okay? So all of the hydrogen nuclei that are aligned with this arrow, B with the subscripted 0, B naught is sometimes what we call this. That represents the external magnetic field, and magnetic fields have directionality. They are vectors, so this would be the north end, this would be the south end. The nuclei that are aligned with the field are lower in energy than the nuclei that are aligned against the field. Now, it turns out that the energy difference between being aligned with the field versus being aligned against the field is not that great. Okay? It's actually really small. If you make some assumptions about what the magnetic field is, magnetic fields are measured in units of Tesla, which has nothing to do with the corporation or its CEO. Then the energy difference between these two states, with versus against the field, is 0.000057 kilocalories per mole. That's like really small. The strength of a bond between hydrogen and carbon is like 80 or 90 kilocalories per mole. So this is a fraction of 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 a percent. Very small difference. Now, you can use, based on this number, we could calculate what kind of frequency of light could excite a transition from one state to the other. And the answer is radio frequency. So remember we talked about UV light and visible light exciting an electron from HOMO to LUMO. That's jumping up about 80 to 100 kilocalories per mole. We said infrared light was good for exciting vibrational transitions. We're now not even infrared or even microwave, we are radio frequency, so fairly low energy light. And it turns out that at room temperature, because this energy difference is so small, there's actually about 50-50 population distribution with the field versus against the field, meaning it's not like this is really even the ground state anymore, because you've got enough energy to evenly populate both states with the field versus against the field. That 50-50 mixture of aligned with versus against is not important right now, hugely important next time. So just put a pin in that and remember that in general, in a magnetic field, about half of the protons are going to be aligned with and about half are going to be aligned against. But then also remember that if you have the right frequency of light, which is going to be radio frequency, about 600 megahertz, you can excite an individual hydrogen nucleus from being aligned with the field to being aligned against the field. And anytime you have a frequency that can excite some kind of transition, you've got a method for spectroscopy. In other words, we're going to shoot radio frequency light at a sample of an organic molecule in a magnetic field, and we're going to see which frequencies are absorbed, that is, which frequencies excite a transition from aligned with to being aligned against. Now, this would be a really boring technique if all protons, all hydrogen atoms, underwent this transition from aligned with the field to aligned against the field at the same frequency. You'd just do the experiment and be like, gee, this molecule has hydrogen in it. Great, that's helpful. But it turns out that this energy gap is highly sensitive to environment. And so protons that are in different environments will have a different frequency of absorption to go from one state to the other. They'll show up at different frequencies, and it turns out that will give us, that combined with some other things I got to tell you about, will give us enough information to deduce the structure of a lot of molecules. Okay, so let me show you what the NMR experiment looks like. We have 2 or 3 NMR spectrometers in this department. They're in the basement. If you take the Organic Lab 455, you will learn how to do this. If you join an organic research lab that does a lot of synthesis, you will learn how to do this technique. But otherwise, I'll just show you briefly how it looks. Your sample goes in a little glass tube that is put in a spin collar, and that collar rotates the sample really fast. That averages out some issues that we don't need to worry about. You put that sample down a tube in this thing that looks like R2-D2 married a moisture evaporator from Tatooine and they had offspring. And what this is a superconducting magnet. So there are lots and lots of coils wrapped really tightly, coils of metal inside this that you charge with a current, and then when current goes through coils, you generate a magnetic field, right? Well, it would be really expensive to have to plug that in constantly, so the coils are made out of a metal that's superconducting at low temperature. You cool down the coils with first liquid nitrogen and then liquid helium. So this is basically a huge thermos, and inside is 4 Kelvin. That's where liquid helium is. And then you charge up the coils once, and because they're superconducting, there's 0 resistance, and so the current circulates indefinitely. But you got to keep it cold, and so people are always going downstairs dumping liquid nitrogen into, there's thermoses inside thermoses. There's a liquid helium thermos, and there's a liquid nitrogen thermos on the outside of that keeps the liquid helium cold. And as long as it's cold, you got a magnetic field. Now, it's a very strong magnetic field, though technology's gotten better, so for the most part, the magnetic field isn't very strong outside a certain radius. In our NMR spectroscopy lab, there are lines on the carpet that indicate where the magnetic field gets above 5 Tesla. Why do you worry about that? Because it will erase your credit cards and will start to tug on metal on your person. It will mess with your pacemaker. And if you have loose metal on you as you get closer, it will rip the loose metal out of you and pull it towards the center of the magnet. So the rule is no metal within this line. And if you have a pacemaker, you get somebody else to approach the spectrometer. Okay, then there's this wire. There's actually a probe that sits around the sample to deliver the radio frequency radiation and observe what happens as a result of that. And then all of that information gets sent to a big box of electronics. It's really quite complicated. And in the end, on your computer, you get an NMR spectrum. Okay, here's an example NMR spectrum. A proton NMR spectrum of the molecule tert-butyl-methyl ether. 1 methyl group here on this side of the oxygen, 3 methyl groups over here on the tert-butyl group. Y-axis for an NMR spectrum is, we call it intensity, and its units are not important. And we'll have more to say about intensity later. On the x-axis is frequency, but again, people were uncomfortable in writing 600 megahertz along this axis, so they found a way to get it to numbers from 0 to 10. And here's the idea. This number is 600 megahertz. That's a 6 followed by all that many 8, 7, whatever zeros. That's not even 7, that's 8. Okay, whatever. 6 or 7. So sorry. The range of frequencies adopted by protons ranges generally from around 600 megahertz to around 600.006 megahertz. So you can see how it would be really inconvenient to have this be 600.006, 600.0055, and so on. Nobody wants to do that. So what they did is they decided to normalize, if you only have about variation of about 6,000 hertz, the way you can normalize this to units that aren't a problem is you take whatever frequency your proton resonates at, you subtract a reference frequency, which is 600 megahertz, you come up with 6,000 hertz, and then you divide by 600 megahertz, and you get 10 times 10 to the minus 6, and then you just replace 10 to the minus 6 with units of parts per million. 1 divided by a million is the same as 10 to the minus 6. And then you can call this frequency 600,000,006,000 hertz, just 10 ppm. Not going to ask you to calculate that, and this is just so that you know that ppm is a frequency of a proton. And you can back calculate out the frequency if you needed to, which you won't. This is called chemical shift, and it's given the Greek letter lowercase delta. We've used that for partial positive charge. We're now going to use it for chemical shift, which is the same as, which is an expression of the frequency at which a proton magnet absorbs radio waves. Okay? So delta in this case just means chemical shift, and that's just a frequency where the proton absorbs. Questions about that? All right, so usually you need a reference compound, and that will show up at 0 ppm. The reference compound is trimethylsilane, and it just has one kind of proton in it, a methyl group. Now you see for tert-butyl-methyl ether, at about 1.2 ppm, you see the protons that are from the tert-butyl group. And at about 3.2 ppm, you see the protons that are from the methyl group. How do we know on the oxygen? How do we know that this peak is characteristic of this group of protons on the carbon that's adjacent to the oxygen, whereas this peak is characteristic of the methyls that are on the tert-butyl group? Two things. First, the frequency or chemical shift, and second, the area under the curve. So right now these look like lines. If we zoomed in, you would see that they are peaks that follow sort of a Gaussian pattern, and you can integrate the area, you can measure the area under the peak. There's a lot of ways you can do this. Computers just do it for you now. Otherwise, you'd have to do calculus, or if you really wanted to, you could cut out the peak and weigh it. Print it out, cut out the peak in paper, and then weigh it and compare it to the weight of other peaks. Anyway, it's silly, but you can integrate the area under the peak, and the area under the peak is proportional to the number of hydrogens represented by that peak. So though the data aren't here, you can see that the peak that represents the tert-butyl group is higher, more intense than the peak that represents just the methyl group. That's because this peak represents 9 protons, whereas this peak only represents 3. And therefore, if you measure the area under the peak, you would expect those to be present in a 1:3 ratio. Okay, right. So with that, that's quantitative information about relative number of protons represented by each peak. Now, so far I haven't given you enough information that you could totally figure out the structure on your own. We're going to do more of that in a little bit, but the other thing I want you to pay attention to is the frequency at which the protons absorb. Notice that the methoxy protons absorb at a higher chemical shift, higher frequency than the tert-butyl protons. Why is that? We're going to talk about that, but I want you to pay attention to the major difference between the tert-butyl protons and the methyl protons. The methyl protons are adjacent to oxygen, which is electronegative. The tert-butyl protons are not adjacent to oxygen. If you want to be precise, what do I mean by adjacent? Well, look at the methyl protons. Each proton is 2 bonds away from the oxygen. The tert-butyl protons, each proton is 3 bonds away. 1, 2, 3 from the oxygen. So, being closer to oxygen makes you show up at a higher frequency. And we'll talk about that. Higher frequencies are sometimes by NMR specialists called downfield for reasons that are historical and no longer matter. Higher frequency, higher chemical shift. We will also call protons that are in this region of the spectrum de-shielded. And it has to do with the fact that the oxygen is sucking electron density away from those protons because of electronegativity. In contrast, protons that show up in this lower frequency upfield direction, we're going to call shielded. So though it's not clear now, it'll be obvious to you later that the protons that are farther from the oxygen should show up at a lower chemical shift or should show up shielded relative to the protons that are closer to the oxygen. Questions about that? All right. So before we dig into the depths of understanding NMR spectra, we need to review molecular symmetry. Why are we doing this? Because one of the things you notice here is I got 9 protons here and 3 protons there, but I only have 2 peaks. Why do I only have 2 peaks? Why don't I have 3 peaks for each proton on the methyl group? They're all the same by symmetry, right? By rotational, you can rotate around this bond and all of the protons can interchange their positions. Same thing with the tert-butyl groups. You're going to see that protons that are identical by symmetry give rise to a single identical signal. Okay? So this molecule only has 2 different kinds of protons, and we only observe 2 different kinds of peaks. So the first thing you need to know when predicting what an NMR spectrum should look like for a molecule is, how many different kinds of protons do I have? Okay. Now, I prepared this for a graduate level class that I taught, and I thought it would be useful to adapt to this class, but I worry that it's going to be more confusing than not. How can I tell if protons are identical or different? First, are they interchangeable by some kind of symmetry operator? Now, I said operator, and that sounds scary. A symmetry operator is a mathematical function, but all we really mean is there some mirror plane or is there some rotational axis of symmetry that can allow 2 protons to change places? If so, if they're interchangeable by a symmetry operator, they are identical. So a simple symmetry operator here is what we call a C3 axis, rotate by 360 degrees divided by 3, or 120, and this proton becomes this one. You see that? Am I good? Okay. Another alternative would be a C2 axis of symmetry, which coincides with this BH bond. If we rotate by 360 divided by 2, or 180 degrees, this proton becomes that proton. They switch places. So both of these symmetry axes would tell you that these protons are identical with each other. Mirror planes could do the same. And you should be better at mirror planes perhaps than you are at rotational axes, because we talked about mirror planes when we were dealing with chirality and identifying whether 2 things were identical or not. For example, a molecule that has a tetrahedral geometry, say a methyl group attached to something else, those 3 protons are interchangeable by rotational symmetry. So they're identical to each other. Okay, I don't think we need, and then we'll do this one. Suppose 2 protons on a CH2 group, where X and Y are individual atoms. The mirror plane that corresponds to the plane of the page here reflects the dash proton into the wedge proton. So you would expect 2 protons on the same carbon, if they are identical via a mirror plane, then they're identical, right? Any questions about that? Yeah?
Can you explain the mirror plane in that one? I'm just not seeing it.
Okay. The purple bonds are in the plane of the page. X and Y are just individual atoms that are not hydrogen. The mirror plane here is the plane of the page. This proton's coming out in front. This proton's going out in back. This proton is a reflection of that one. Got it? Yeah. Okay. So that's pretty easy. It turns out there's a couple other ways that you can use to identify protons that are identical to each other. Oh, shoot. What we're going to do now is apply these principles in different structural contexts to see when protons are identical to each other versus not. You're going to see there are 4 different categories of proton relationships. Protons can be homotopic, which means they are always identical. Protons can be enantiotopic, which means they are identical if in an achiral environment. You can have protons that are diastereotopic, which are different. And then you can just have protons that are different. We'll say diastereotopic. They are different, but they are stereochemically related. And then you just have protons that are fundamentally different. The example that we saw earlier, the protons on the methyl group are homotopic with each other. The protons on these three methyl groups are homotopic with each other. The A and B protons, this methyl group versus the tert-butyl group, those are just plain different. Okay? So let's talk about what we mean by homotopic. Protons that can be interconverted by a rotational axis of symmetry are called homotopic, and they are always identical, meaning they give rise to the same NMR signal. Classic example of homotopic protons is the two CH2s in propane, HA and HB. You put an axis down the plane of the page through this carbon atom, you rotate 180 degrees, and HA and HB trade places. They are homotopic, they are always the same. There's no difference between the two of them. Similarly, on this molecule, which is chiral, we have an axis of symmetry that goes through this carbon and halfway through this bond. If you rotate around that axis, methyl group A and methyl group B trade places, and phenyl group C and phenyl group D trade places. When we rotate around that axis of symmetry, we have exactly the same thing. So therefore, methyl group A and methyl group B are homotopic, always the same. We would get just one signal. And then phenyl group C and phenyl group D, benzene rings C and D, are also identical to each other. All right, so some of the skills you developed in the early part of this class about chiral or not, are these two things different or not, is this a stereocenter? Those will help you here at identifying protons that are the same, homotopic. Enantiotopic protons are kind of interesting. Enantiotopic protons are any two protons that are interconvertible by a mirror plane. So HA and HB here, there's no longer a rotational axis of symmetry that'll interconvert A and B. HA and HB are interconvertible by a mirror plane. That means they are what we will call enantiotopic. Now, for our purposes, enantiotopic means identical unless you're in a chiral environment, which means that a protein could sense the difference between HA and HB because a protein is chiral. And when you get to biochemistry, you will see a protein selectively remove one of two enantiotopic protons. Okay, so what's the difference between enantiotopic versus homotopic? Homotopic protons are interchangeable by an axis of symmetry. Enantiotopic protons are interchangeable by a mirror plane of symmetry. How are you going to remember that? Well, remember enantiomers were mirror images of each other, and so maybe that'll help. Okay, you've seen meso compounds like this that have a mirror plane of symmetry. HA and HB are therefore enantiotopic. They're identical, except in a chiral environment, a protein could tell the difference between these two. The OH groups are enantiotopic. The methyl groups are enantiotopic with each other. So this term enantiotopic is a relationship between two protons or two groups, and it means they're identical unless you're in a chiral environment. Yes?
Is that entire atom homotopic?
The entire molecule?
You rotate the whole thing.
Sorry, what entire atom?
Yeah, sorry. What?
I'm confused. I'm confused, and because I'm confused, you're confused. The whole compound has a mirror plane of symmetry. We wouldn't describe, an antiotopic is always about a relationship between two things. So just like you can't look at something and say, is it an enantiomer? It's like, is it an enantiomer of that? And the same thing, you can't say, is this one thing an antiotopic? You have to say, is it an antiotopic to that other proton? Yeah.
So then would hydrogen A and hydrogen B be homotopic or enantiopic?
Enantiotopic, because they're interchangeable by a mirror plane of symmetry and not an axis.
Can't we rotate the molecule? Because if we look at it from backside, it would
Nope, if you do the C2 pancake flip, you don't get exactly the same thing. By interchangeable, we mean everything looks the same and ends up in the same space. And if you do the rotational axis, you get this, which doesn't look exactly the same. Now, I agree with you, it's clearly the same molecule, but the symmetry operator that tells you that HA and HB are the same is this mirror plane of symmetry. Okay, we're doing this because in 353, Dr. Bronson, when you take that lab, is going to push you on homotopic and antiotopic and diastereotopic. And this was hard for me to get, and so I wanted to help you out with it. Okay, protons that cannot be interconverted by a symmetry operation are always different. And when those two protons are on the same carbon, we call them diastereotopic. So here is a molecule that has OH at a stereocenter, and I'm going to highlight the stereocenter. The presence of the stereocenter means that there is no longer a plane of symmetry that reflects HA into HB. Why? HA on this side of the page experiences being close to the OH group. HB on that side of the page doesn't. The presence of that stereocenter makes those two environments absolutely different. Somebody doesn't believe me, so raise your hand and ask. Okay, you don't care, you're just going to accept it on faith. Good. So, protons that are on the same carbon, CH2 protons, you're going to be tempted to think, oh, they're always identical. But these two protons on the CH2 group cannot be interchanged by a mirror plane because of this stereocenter. Therefore, they are diastereotopic, meaning they could give rise to distinct NMR signals. Therefore what? Well, we'll talk about examples of that later, but at least at the beginning, it's useful when you look at an NMR structure to have a hypothesis about how many different kinds of protons you should expect to see. And therefore, recognizing protons that are enantiotopic, like here, in ethanol, these two protons should show up at the same chemical shift, same signal, unless they're in a chiral environment. So those two are identical to each other. And these homotopic protons in propane are identical to each other. But these diastereotopic protons in this chiral molecule are distinct and different from each other. So, quick way to remember it, quick thing to memorize if you don't want to think about symmetry is if the molecule is chiral, CH2 protons are diastereotopic and different. If the molecule has stereocenters, if the molecule is chiral, CH2 protons are different. Also, methyl groups can be different. So this is an amino acid called valine. It has a stereocenter. These two methyl groups are diastereotopic. They're not identical because there's no plane of symmetry that could exchange the two of them. Okay, if you want to dig more into enantiotopic, diastereotopic, and homotopic, look at the notes. There is method 2 for doing it. This works, but I've generally found that it is confusing to students. So if it helps you, you can look at it. All right. Why are all the answers drawn there? I can't ask you questions. Okay, hold on just a second. Blank. Dang it. I'm going to draw a structure real quick, and then we're going to talk through which protons are identical. I shouldn't have put all the answers in. Behold. So, let's talk about these 3 methyl protons. 1 signal, 3 signals? 1. Are they identical to each other? Yeah, and I would call them homotopic, enantiotopic, or diastereotopic to each other. Homotopic, that's because they're interchangeable by rotational symmetry. Good. All right, and that would apply for these too. What about this methyl group and this methyl group? Should they show up at the same or perhaps different chemical shifts? They have different environments, so you expect them to be different. We'll call this A, we'll call this B. How about these 2 protons? They're the same. Are they, what kind of same are they? Are they homotopic or are they enantiotopic? So they are interchangeable by a mirror plane, but they're interchangeable by a C2 axis of rotation, which is the pancake flip. If they're interchangeable by the pancake flip, they are homotopic. So they're both protons C, homotopic. Okay. How about these 2 methyl groups? Same or different? Same. What kind of different? What kind of same, rather? Homotopic. Good. All right. You're getting there. We'll pick this up on Monday. Have a good weekend. Get some rest. We'll see you then.